Hello, and welcome to this tutorial to the quantum circuit generator powered by the group leader optimization algorithm. At the very beginning, here's a side note that we already developed a tutorial notebook file in terms of Jupyter notebook file that include all the commands, instructions, and comments that help you to run this quantum circuit generator by yourself. So feel free to check it out. Okay, going back to the tutorial. First, what is a quantum circuit generator? It is a generator that takes in the unitary matrix as input and have a quantum circuit as the output, so that the generated quantum circuit, if you write it in a matrix form, it will be very close, well, in the ideal case, equals to your target matrix. Here are one examples. We have an 8x8 unitary matrix. A very popular or widely used circuit generator is the QSCID transfer function. And the QSCID is a package developed by the IBM Quantum to facilitate the quantum programming and quantum computing. And this QSCID transfer function will take this 8x8 unitary matrix and build a 3-qubit quantum circuit out of it. Okay, going back to our quantum circuit generator. Our generator will do the same job, that it will have a unitary matrix as the input, and it will give you a quantum circuit as the output. But it uses the GLOA to facilitate it. And in our quantum circuit generator, the user can choose whatever the universal gate set it wants, or can even define his own quantum gate or define his own personalized quantum gates. Using this generator, the user can choose the circuit depth, which is the number of quantum gates you want in the quantum circuits, the iteration limits, and can also set up the variation ratio, which should give you some extra control power in the optimization process. And finally, the GLOA will optimize the circuit to gain the minimum cost. That is, to build a quantum circuit that has the lowest fidelity error and the least number of quantum gates. Okay, next, let's talk about the GLOA schemes. The GLOA beginning will generate a large number of candidates. In our case, will generate a large number of randomly generated quantum circuits that follows the basis set which is decided by the user, and also the circuit depth decided by the users. Then the GLOA will divide those candidates into groups that have same number of members within. And by dividing them into groups, the GLOA can process each group in parallel and thus saving some computational time. Then the GLOA will evaluate the cost function of each member, and they will pick up the member that has the lowest cost as the group leaders. Choosing this group leader will have a better direction on how to vary the other members of the group. It's like we'll vary the member according to the best performed member of the group. Okay, next, let's talk about the fidelity error and what is contributing to the cost. First, for a candidate approximation circuit U of A and a given target unitary matrix U of T, the trace fidelity is given by F, which is taking the trace of UA times UT dagger and divided by N, which is the system size. So in the ideal case where UA equals to UT, F will be equals to 1. So the fidelity error used in this optimization is epsilon equals to 1 minus F squared. We're taking a square to the F so that we can amplify the changes in the F. And it will be better reflected in this epsilon. Another contribution to the cost is the number of gates. And to our definition, 1 qubit case has a cost of 1, and the control gate, which is 2 qubit gates, has a cost of 2, respectively. So then the cost of the circuit is found by summing up the cost of the gates composing the circuit. So our GLOA will try to reduce the cost by lowering the fidelity error and lowering the number of gates needed. Next, let me show you the flow chart of our quantum circuit generator. After we start it, we will generate a lot of randomly generated quantum circuits as our candidate. And then we'll create n number of groups and generate and evaluate the initial population for each group. Then the GLOA will evaluate the cost function of each member and then choose a group leader for each group. Next, we'll do the variations, and we'll create a new population following these rules. Each new member will keep a portion of its own, and it will keep a portion from the group leader, and then finally keep a portion that is randomly generated. And this ratio by default is R1 equals to 0.8 and R2 equals to R3 equal to 0.1. After this variation, this GLOA will actually reevaluate the member. And if any member outperforms the group leader, this outperformed member will be the new group leader. And this serves as a very full iteration. And at a given number of times, we'll actually do a parameter transfer, which is a one-way crossover for each group to the other groups. In this way, we'll let each group talk to each other. And then we'll evaluate all the members in the groups, that is the whole population, and to see if it's met our termination criteria. That is, if it is reached to the cost, to our target cost, or we have used all the iteration numbers. So then if it met the criteria, it will terminate and return the member that has the best performance. Okay, next part, let me guide you to the coding session. And hopefully I print out the most essential command that you want to use when you try the Jupyter Notebook by yourself and make it easier for you. The first step is always declaring the package we want to include it, such as a NumPy package. And then all of these functions are very useful and important functions to do this GLOA iterations. First, this GLOA function serves as a core function of GLOA. And this QDIS is a mathematical function that helps measuring the distance between the target and the generated as part of the cost function. This QUpConstant function actually records all the default quantum gates. This QTimeit function will keep track of the runtime. This QCirc function have all the tools and all the instructions on how to build the quantum circuits and vary the quantum circuits. This QUp function has the operation of the quantum gates. Finally, this QTypes records the data type used in this program. I'm telling you this function because if you want to modify this program, say by adding some custom gates, you want to actually look into the file name that includes these functions, and feel free to modify and make it more powerful. Okay, the first step is declaring the quantum gates. You actually want to define the basis gate set you want. Currently, the supported gates include the X, Y, and Z gates, the phase gate written as S, the Hadamard gate written as H, and the pi/8 gate written as T. It also includes identity gate, control NOT gate, rotation X, rotation Y, rotation Z, and finally SX gate as the square root of X gate. Okay, in our example, we choose the basis to be SX gate, RZ gate, and CX gate. Next, for some of the gates, that don't have a free parameter such as SX gate, CX gate will input the value none for the bounds. And for RZ gates, you have a free rotation angle. We set up the boundary to be 0 to 2 pi. Finally, we'll keep a little timer for ourselves to keep track of the runtime. Next step is enter the unitary matrix you want. You will enter the matrix in terms of NP array. And finally, we do the approximation. We run this core function that is GLOA.groupLeader. In this function, this U is the matrix you enter, it's a targeted matrix. This length is the number of gates allowed. Notice that this function not necessarily use all of them, it's like the upper bound. N is the number of groups, and P is the number of members inside each group. We already defined the basis and the boundaries in the previous steps, and the max iteration is set up the max number of iteration allowed. And finally, this R is the rate that determines the portion of the old, the leader, and the random that are used to generate the new candidates. If this part is kept blank, it will use the default value as listed here. Okay, and then you will run the function and it will do the iteration and return you this U approximated to be the circuit that is generated. We actually write a very handy function called toQskit that will turn this U approximate into a Qskit function, into a Qskit circuit object. And so you can use all the handy visualization tools from the Qskit package, such as .draw, to draw the quantum circuit to give you a better and more straightforward way to see the quantum circuit you generated. Since we're using the Qskit function, so make sure you properly install and configure the Qskit package before running this program. And this marks the end of this tutorial. And thank you very much for the listening.